So yeah, let's wait for 2 or 3 minutes. Let's see how many people join. Then you can start. Okay. Let's. Okay. Let's start without wasting our time. Uh, okay. So maybe we shall start with an important problem that is given in your practice sheet. Uh, let K be a field and let us denote K by K as the set of all functions f from K to K. Now let epsilon be a map from Kx to K to K by if f is a polynomial of Kx, then it goes to a function which sends t to f of t. That is where your t is from K. Now observe that epsilon is a K linear map, right? And how to check this? Now suppose you say epsilon of a plus alpha g, where your f and g are coming from K of x and alpha is coming from K. Then this should map to a function. Say suppose this function is denoted as a prime as K to K, where your a prime belongs to K to the power K, such that a prime of t equals to ft. Okay. Right? So this would be my a plus alpha g prime. Now let's look at this map. A plus alpha g prime of t should be f of alpha g of t. Now this simply implies f of t plus alpha of gt, which again gives you f prime of t plus alpha dot g prime of t. So which you can write it as a prime plus alpha g prime of t. So this simply gives you a prime plus alpha of g prime, which implies epsilon of f plus alpha of epsilon of g, right? So these kind of things I guess you are already comfortable with. Now there is a so our aim is to prove that first goal is to prove that this epsilon is injective if and only if k is infinite. K is infinite means cardinality of k is infinite. That means that k has infinite number of elements. So let us start proving this. So let me stop if you have any doubt or if I make any mistake. So yeah, the inverse direction says something like this. Let k be infinite and epsilon of f equals to epsilon of g, that is f of t equals to g of t for every t of k. Then we'll see that h, which you can write it as a minus g, something like this. Then for h minus g, h of t equals to 0 for every t of k. That is, h has infinitely many roots. But you know that a non-zero polynomial suppose say ht from k x, say x here. Okay. A non-zero polynomial hx of degree n has at most n roots in k, right? So this is something you know from your high school and everything. So therefore h is 0, right? Because if h is non-zero, then it would have a like fixed degree, that is it would be constant or something, like it has positive degree or anything. But then in that case, either if it is constant then it has no root, and if it is like have positive degree then it would have finite roots. But in any case, if h is non-zero, then it should not have infinitely many roots, right? So therefore h is 0, and this would imply that f equals to g. So hence so h injective. Note that this fact uses this, that k is infinite. Because the question of infinitely many roots only comes when the field itself has infinitely many elements, right? Okay, so let us start proving the sorry let us start proving the uh, the forward direction. So for contradiction, suppose uh, say uh, k is finite. So we'll show that if k is finite, then epsilon cannot be injective. Say k equals to t1 up to tq with cardinality of k is q. Now put fx sorry put your fx as x minus t1 into x minus t2 to x minus tq. Then you can see that f not equals to 0, right? One second. Yeah. Because it is monic of degree q. But f of ti equals to 0 for every I or belongs to 1 to q, right? That is f equals to 0 in like say that means you can say something like this. So epsilon of f equals to 0, right? Because epsilon of f you took something like this. Where your elements are coming from this, it is your t and it is of the form ft. So epsilon of this t is 0 for f of t is 0 for every t of k. So epsilon of t is 0. That means your epsilon of f is 0, but where f is not 0. So epsilon is not injective. So this is your contradiction, right? So you can finish this by saying one line that therefore if epsilon is injective, then k is infinite. So we finish our proof here. Now we go to next proposition that says epsilon is surjective if and only if k is finite. So you can, if this is true, if we can prove this, then you see that it can, epsilon can never be bijective, right? Because a field cannot be both finite and infinite simultaneously. So yeah, but again it will be again always injective or again always be surjective, because a field always will be either finite or infinite, right? So uh, there is something called Lagrange's polynomial. uh, Maybe I should write it first before proving this. uh, so maybe we should start doing that. Lagrange interpolation formula. So I'll not be doing the proof here, but you can look into some textbook or internet to find standard proofs of this. Uh, so yeah, let a0 up to an of k uh, be distinct elements, and b0 up to bn k be given. So you are saying, you are only assuming that a0 to an are distinct, but b0 to bn you can take anything. Then define something like this: if as summation of I0 to n bi by ci product your j coming from 0 to n minus I x minus aj, where ci equals to product of ai minus aj, say j not equals to I. Is the unique polynomial of degree less than equals to n, such that f of ai equals to bi for all I belongs to 0 to n. So you have to keep this in mind, that this theorem says that this is not only a polynomial. You can clearly see that f of ai should be bi, because your ci is the all other elements which which cancels out this product x minus aj, and but this theorem says that not only this is a polynomial, but this is only polynomial. Okay, so maybe I should take this to new page and keep this formula here. Okay, so now I think we are ready to prove this, that okay, 1 second. Okay, so let us prove the negation first. uh, let k be your finite field, that is a0 to an be finite uh, with with the ai distinct, and and let f equals to k to k be any function. Now you set bi as f of ai. Now you uh, you already took a0 to an the elements of k, so therefore they are distinct, and you are taking a function from k to k, and you are setting bi as f of ai. Then you can take the Lagrange polynomial that we saw earlier, that take Lagrange polynomial uh, if as this again I0 to n bi by ci, and this is product of x minus aj, j not equals to I, and your ci also product of ai minus aj, j not equals to I. So yeah, so what we uh, get is that from Lagrange's interpolation formula, it says that uh, this maybe I should write it as capital F. This f is the unique polynomial of degree less than equals to n, such that fai equals to bi. Now you already had f in your hand, which is a function, and you take f to be this polynomial. So therefore you can see that epsilon of f should be this small f, right? From Lagrange's interpolation formula. Now if you don't have any doubt regarding this, can you think of the forward direction? That So the inverse is little tricky, but it does not need any big formula, or at least what I think. uh, so what we will show that if k is infinite, then uh, this epsilon cannot be surjective. So for contradiction, let k be infinite. Fix small a belongs to k and consider a function, consider del a k, where your del a is k to k such that uh, your del a of a equals to 1 and del a of t equals to 0 for t not equals to a. That is, only it takes a to 1 and other elements to 0. So if del a equals to epsilon f for some f belongs to kx, I mean, if epsilon was surjective, then for del a it would have some f of kx such that epsilon f equals to del a. Then what would happen? Then f vanishes on the infinite set k minus a, right? Because your del a of because del a of t, which is epsilon of f of t, that is f of t, will be 0 for t not equals to a, right? That is what I am trying to say. So f would have infinitely many roots, but that is only true when f equals to 0. Therefore f equals to 0, but then del a of a, that is f of a, would be 0, right? But we already took del a to be 1, so contradiction, right? Therefore, so del a is not in the image and epsilon is not surjective. Right? So please let me know if you have any doubt regarding this. So till now we have proved that we have a function epsilon from kx to k to the power k, where k to the power k we denote as set of all functions from k to k, and we show that epsilon is injective if and only if k is infinite, and epsilon is surjective if and only if k is finite. So I guess this gives you some idea to how to tackle these problems for exam or assignments. But now let's move on to our next problem. But these will be short problems, so I will suggest you try for 2-3 minutes first, then I'll do the solution, because that way it will be more engaging. Okay, so let me write the problem first. So this is your main problem. For A or B of R, the straight line L A comma B, which are elements of R2, such that Ax plus By equals to 0 from R2 are subspaces of the R vector space R2 so first we have to show this, then but for C of R such that C not equals to 0, the straight lines, the lines L A comma B comma C xy of R2 such that Ax plus By equals to C of R2 are not subspaces of R vector space of R2. So it is a calculative problem, so maybe you should try it first, then maybe you already know the subspace criterion, right? Because in the last tutorial we discussed this. So it says something like this. Yeah, so you can see it. Subspace criteria. W of V is a subspace if and only if alpha W1 plus W2 belongs to W for every W1 W2 belongs to W and for every alpha belongs to K. Your K is field. Maybe you should try this for 2-3 minutes, then we will. Yeah, okay. So let us try to solve this. So first of all, this subspace criteria what we have. So let x1 y1 and x2 y2 belongs to uh, L A comma B, and alpha belongs to K. Then see if then A of x1 plus alpha x2 and B of y1 plus alpha y2 equals to ax1 plus by1, right, and alpha of ax2 plus by2. And since x1 comma y1 was taken from LA comma B, then ax1 plus by1 equals to 0, and similarly alpha dot 0 equals to 0. So this is 0. So x1 plus alpha x2 comma y1 plus alpha y2 belongs to LA comma B, which implies x1 comma y1 plus alpha of x2 comma y2 belongs to L of A. So the first case, that is L A comma B is a R subspace of R2, is proven, right? Now the second case, can anyone tell me why it cannot be a subspace? For the second case, you don't have to check the subspace criteria. A simple observation can show you that it is not a subspace. Can anyone tell me? Uh, can you see that if 0 belongs to this LA comma B comma C, because a subspace should contain 0, right, a unique additive identity element, and an identity element should be same as in the original vector space and the subspace also, right? So in the original vector space in R2, identity element was 0 comma 0, so it should be also the identity element of LA comma B comma C, right? But if 0 comma 0 if 0 comma 0 belongs to LA comma B comma C, then 0 dot x plus 0 dot y would be C, right? Therefore C would be 0, but C not equals to 0, right? So LA comma B is not a subspace. Okay. So let us come to our next problem, that is okay, let me write it down. The subsets U equals to x comma y of R2, where x square equals to 4xy minus 4y square, and u prime equals to x comma y as x square minus 4y square equals to 0 are subspaces of the R vector space R2. So, can you prove this? So, I am already asserting that these are subspaces. So, you only have to use this subspace criteria. Then I should write it here. Yeah. See, can you do this? So, check if they are subspaces. Subsets. Okay, so let us start doing this. So for the first problem, you see that the subset U uh, x comma y of R2, which is x square equals to 4xy minus 4y square, and if you take this equation, it can be rewritten as minus 4xy plus 4y square equals to 0, right? And this is something equivalent to saying x minus 2y square equals to 0, and this is equivalent to saying x minus 2y equals to 0 and x equals to 2y. So interestingly, u can be written as x comma y of R2 such that x equals to 2y, that is 2y comma y, where your y belongs to R2, so can be written as R of 2 comma 1, right? So u is a line passing through center and 2 comma 1, so u is a subspace, because every line passing through the origin is a subspace, right? Now let's look at the second problem, that is u prime equals to x comma y of R2 x square minus 4y square equals to 0. Can you say something like this? If you check if you take any two numbers satisfying these two equations and see if their sum belongs to this, something like these kind of arguments. All right. So see that 2 comma 1 and 2 comma minus 1 belongs to u prime, right? As 2 square minus 4 into 1 square is 0, and 2 square minus 4 into minus 1 square is 0, right? But 2 comma 1 plus 2 comma minus 1, which equals to 4 comma 0, and 4 square minus 4 into 0 equals to 16. So 4 comma 0 does not belongs to u prime, right? So u prime is not closed under addition, and therefore prime is not a subspace. Right? Okay. So let us go into the next problem. Okay, so this will be our next program. For subspaces, uh, U and W of a vector space V over a field K so that the subset V minus U minus W is a subspace of V if and only if either U equals to V or minus W. So can you try this? So let us try this for 2-3 minutes, then we can. Okay, so let us start solving this. So for the converse direction, if U belongs to W, I mean U is a subspace of W, then sorry, then u minus w is empty, right? So uh, what would happen is that v minus mt is v, which would be a subspace, right? Now if u equals to v, then what would happen? Then v minus u minus w should be v minus w, which would be something like w, right? As w is a subset of v. So yeah, again a subspace. Now we look into the forward direction. Suppose S is a subspace and for contradiction u not equals to v and u not a subspace of w. Now choose small u belongs to u minus w. This is possible since u is not a subset of w, and take v from v minus u. Again this is possible since u not equals to v. Then you can see that small u belongs to u minus w, so small u does not belongs to S, and if you look at it also small v does not belongs to u, hence small v does not belongs to u minus w, that is small v belongs to S. Now next look at it that u plus v does not belongs to u. I mean if it was otherwise, v equals to u plus v minus u of capital U, contradicting the choice of v. Therefore small u plus small v belongs to does not belongs to u minus w, that is small u plus small v belongs to S. But S is a subspace and small v belongs to S. So small u equals to small u plus small v minus small v belongs to S, contradicting small u does not belongs to S. Hence E equals to V or belongs to W. Right? So please let me know if you have any doubt regarding this, because I have been constantly talking and you guys are not asking any questions, so I'm not sure if you are taking this clearly or anyway. So let's look into our next problem, but I guess you should try this first, because then only I can understand that at least you guys are trying. So again, U and W are subspaces of V, and if U union W equals to E plus W, then we have to show that either U belongs to W or W belongs to U. Okay. So so one direction is clear, right? That uh, both u uh, I mean for small u belongs to capital U plus 0 equals to u. Uh, it, it belongs to u plus w, right? Just a small w. So u belongs to u plus w, and v belongs to u plus w, right? And now suppose uh, for contradiction assume that u does not belongs to w and w does not belongs to u. Then we can pick small u from u minus w and uh, small w from w minus u. Then u plus small w belongs to u plus capital W, which equals to u union w, right? So either u plus w belongs to u, hence small w equals to u plus w minus u belongs to u, which is a contradiction to the fact that w does not belongs to u, and or u plus small w belongs to capital W, whence small u equals to small u plus w minus small w, so w. Contradiction as small u does not belongs to w, hence u belongs to w or w subset of u. Alright, so next we focus on some interesting um, exercise that says that prove that the set W even uh, respectively W odd of of all uh, even functions R to R and respectively odd. Yeah. So since R to R is a R subspace of R to the power R and W even intersection W odd equals to 0 and W even plus W odd equals to the power R. That is set of all functions from uh, R to R. Again, I think you should try this for some time, then again you will try. So first I recall two definitions. Recall that f from R to R is even if f of minus x equals to f of x for all x belongs to R and odd if f of x equals to f of minus x is to minus of fx for all x belongs to R. So please try to show first that W even and W odd are subspaces, and then we can try doing both, that their intersection is 0 and union is all of. Okay, so let us try solving this. So first we have to show that W even, and similarly W odd is a subspace. Uh, Now you can take uh, let F and G are from W even and alpha belongs to R. Then alpha F plus G of minus x equals to alpha of minus x and G of minus x, which is same as alpha of fx plus g of x, and this is equals to alpha of f plus g of x. So alpha f plus g belongs to W even, right? And so the subspace thing we are done. Now the more interesting part is that we have to show that their intersection is 0 and their sum is the whole space of functions. Now let f belongs to W odd intersection W even. Then for every x belongs to R, we have f of x equals to f of minus x since it is even, and minus of fx since it is odd. This would imply 2 of fx equals to 0, right? So f of x equals to 0, and which imply that that is W odd intersection W even is 0. Now let us try to prove the third part, that is their sum is R to the power R. Now given any f of R to R, define gx as f of x plus f of minus x by 2 and h of x as f of x minus of f of minus x by 2. Then observe g of minus x as f of minus x and f of x by 2, which is nothing but g of x, right? And h of minus x is to f of minus x minus f of x by 2, which is nothing but minus of hx. So g is even and h is odd, which gives us that every element can be written as sum of and one more thing, f can be written as f of x plus f of minus x by 2 plus f of x minus f of minus x by 2. So R to the power R, where f belongs, is contained in W odd plus W even, and it is trivial to show that W odd plus W even is a subset of R to the power R, so they are equal. W odd plus W even, and that is what we are supposed to prove, right? Yeah, so we are done now. Okay, now we can uh, try to prove this, that is uh, uh, the set of all functions if C to C with limit z tends to infinity, if z equals to 0, is a subspace of the vector space C of C. This can you try it? So maybe we should write down what do we mean by this. So this means that for every epsilon greater than 0, there is r greater than 0, such that mod of fz is less than epsilon whenever mod of z is greater than r. So maybe we should try proving this. Oh, this should be less than. Oh no, this should be greater than, because it says z goes to infinity, not z goes to 0. Okay, so let us start solving this. So yeah, obviously if z is 0 is one of them. uh, Such that limit z tends to infinity if z is 0. Now uh, take f and g uh, from c to c such that limit z tends to infinity f and limit z tends to infinity gz equals to 0. Now choose like for epsilon greater than 0, choose R1 with fz less than epsilon by 2 for mod z greater than R1, and R2 greater than 0 with gz less than epsilon by 2 for mod z greater than R2. Now for mod z greater than max of R1 comma R2, we have f of f plus g of z less than equals to of fz plus g of z less than epsilon by 2 plus epsilon by 2 to epsilon. Hence f plus g belongs to z, right? Again, now if a belongs to c, then if a equals to 0, then a dot f equals to 0. So there is nothing to show. Now if a not equals to 0, then for epsilon greater than 0, choose r greater than 0 with fz mod of fz is epsilon by a for mod z greater than r. Then mod of af of z equals to mod of a dot f of z. So less than epsilon for mod of z greater than r. Hence f of f belongs to z. So yeah, so z is a subspace of. So yeah, we are done with this problem. Okay, so there are still some problems left which which I leave you for exercise. Uh, okay, maybe we should do another problem and then we can leave it. Uh, let v equals to r of with a k vector space, uh, with a r vector space. Uh, determine no let w be the uh, of all polynomials ai zi, sorry, ai x to the power I 0 to n, such that ai belongs to z, uh, and w2 is I 0 n bi x to the power I, so bi belongs to R. Check if these are subspaces. So again, you should try this for 5 minutes, then you can start discussing this. Okay. So for the first one, take alpha from r minus z, which is not an integer, uh, or irrational numbers, then one can show that W1 is not closed under is not closed under scalar multiplication, and the next one is a subspace. uh, in fact, W, you can check that yourself. W2 is a subspace. Okay, all right. We'll finish here today, and we'll meet in the next class. So yeah, good night.